you've had some time now to let the amazing power of the fundamental theorem of calculus sort of wash over you. So now that you've got that at your fingertips, let's take a look at using it to do something that you might not have thought about trying to do before. Averaging a function. So we know how to average like a what you might call a discrete set of numbers. You add them all up, you divide by however many you have. For a continuous function over an interval, it turns out the definite integral gives us a way to take a look at precisely that, and then we can use the fundamental theorem to work out said definite integral if our function's nice, which for this course they generally are. Okay, so I generally abbreviate that F with like a subscripted AVE. It's not really supposed to be fave, but it ends up looking like that. I don't think our text uses that notation. I don't know if it gives a notation at all. So anyway, so the idea is if you know your function's defined over some interval, AB, we need to divide by the length of the interval, so 1 over b minus a, and then sitting in the back, we'd have the definite integral of our function from a to b. So pretty straightforward. You know how to work out a definite integral, you really just need to divide by however long that interval you're integrating over is, and you're good to go. So let's take a look at an example here. All right, so got a quadratic function here, x squared minus x, and we'll focus on the interval from -1 to 1. So a, b, f of x. We can fill in the blanks and go to town. So 1 over 1 minus -1. Again, if you would just jump straight to 1/2, I get it. Okay, so just filling in the blanks. Now, fundamental theorem says we find an antiderivative of this sucker and then work out the difference of its values at each endpoint. Okay, so don't forget that 1 over b minus a thing hanging around out front. Sometimes students write it here and then they get so caught up in the calculus they forget about it. So anyway, so I got the 1/2. My antiderivative, thanks to using the power rule a couple of times, would look like 1/3 x cubed minus 1/2 x squared. Evaluate that at 1, evaluate that at -1. If I work this thing out at 1, I get 1/3 minus, what, 1/3 minus 1/2, right? So that's, so 1/3 minus 1/2, that's 2/6 minus 3/6. Yeah, so -1/6. Minus, if I plug in -1, well, this is -1/3 minus 1/2, so that would be, now you have 2/6, -2/6 minus 3/6, so we get -1/6 plus 5/6, that's 4/6 or 2/3, 1/2 of 2/3. I'm out of room. I'll write it over here because I have the marker. Okay, so our average value in this case works out to be 1/3. Okay, so average value. If you know how to compute a definite integral, and with the fundamental theorem, frankly, you should be like jumping at opportunities to evaluate definite integrals now because it's great. I guess I'm weird. I find it exhilarating. So there was something else I wanted to take a look at, but this board needs to get cleared first. Okay, so you might remember if you've talked about averaging numbers before, another word for an average is a mean. So, yay. It turns out our friend the mean value theorem has an analog that applies when we're dealing with integration as well. The mean value theorem for integrals. It's sitting right there behind me. I don't know why I felt the need to read it out. Anyhow, so the idea is same setup. We assume f of x is continuous. We don't need differentiable this time. Don't worry about that. All you need is that f is continuous on AB. So we must have at least one number c, technically. There could be multiples, but we have to have at least one number c inside our interval from a to b. And it turns out you can write the conclusion a few different ways, but that's really what it boils down to. F of c has to equal our average value. So, yeah, I like looking at it that way, because then it kind of pulls in that whole, mean value, average value thing. Okay, so let's revisit our example from just a moment ago. So we got x squared minus x. Our interval was -1, 1. We found out that average value was 1/3, so according to the mean value theorem, there has to be at least one number c sitting inside here that gives us c squared minus c equals 1/3. That's a quadratic equation as far as c is concerned. So we've got to rearrange it so c is all the terms are on one side. We've got 0 on the other. I'm going to go ahead and get rid of the 1/3 just because I think it looks nicer if it looks like that. So 3c squared minus 3c minus 1 equals 0. I will save you heartache now. Do not try to factor this thing. It's not designed to do that. You can use the quadratic formula. Full disclosure, I just graphed this thing in my calculator and then used the 0 command to track down the c values where this ends up being true. So I got one c value of negative 4 decimal places I'm giving here, 2638, and I've got c2 of 1.2638. So those are the c values that satisfy this. There's a catch. Do both of these guys live inside the interval we need? No, they do not. This one is outside there. Slash. He is not in there. So since that's not in the interval, forget him. He doesn't matter. He's not what we're interested in. That's the guy we're interested in, this negative 0.26 guy. All right, so before I draw this video to a close, I wanted to take a look at something in terms of like a picture of this. But again, this board is full of stuff, so bear with me. So here's a picture of what's going on as far as the mean value theorem for integrals is concerned. So you may recall we had something kind of similar with the first mean value theorem, where we had like a secant line and a tangent line running in parallel to each other. There's an analog. It's not like a one-to-one thing. But so I've got my graph of my quadratic here. So it crosses the axis at 0 and 1. It dips under a little bit right there. And we've got it poofing back up. It's not quite to scale because this should be like 2 units high, but, bear with me. So anyway, so remember the definite integral that we worked out would have basically been this positive area over here minus this area that's getting captured underneath the axis. That's what the definite integral does for us. So what the mean value theorem for integrals basically ends up saying in terms of the picture is the following. So you'll remember my c value was somewhere in that ballpark. It was about a quarter of the way over. It was like negative 0.26. So that's not a bad estimate. So the idea is if I go back up to that point and draw myself a rectangle using that height, that rectangle should capture the same area that my definite integral does. So that kind of stands to reason. If you imagine trying to like fold this stuff over, you can see this kind of cancels out some of it. So the picture does a decent job. It's actually a little clearer if the function is above the axis completely. It's easier to draw. But this was the example I had to work with. So that's average values. We got to work with more definite integrals, which is fun. I've got one last example I want to take a look at, and it's a bit of a doozy. It's okay. We'll get through it.